Hi, so today we are going to discuss about zero phase transfer functions. What are they? Um, so let's first discuss the concept of phase distortion. So what is phase distortion? Basically, you have a signal. It's like a square wave, right? It's a square wave approximately, and it has got different, so it consists of three frequency components. One is 5 hertz, let us call it as F naught. This is 15 hertz, let's say 3F naught. This is 25 hertz, which is 5F naught, right? And there are some amplitudes so that it looks like approximately a square wave, right? But now if I pass it through a filter which does nothing, but just introduces one phase shift at just one frequency. So this phase shift depends on omega, and with respect to only one frequency, it has caused a phase shift. It means when I say F naught, it is 2 pi F naught. You understand this, right? This 2 pi is understood. Okay. Um, so this is phase shift, which is dependent on the frequency. And what you see is you get a distortion because only one frequency got shifted and other frequencies are still the same. So you get distortion. It no longer looks like a square wave, right? How to avoid it? So there can be two solutions. One is that your phase shift, we call it as delta phi, is equal to 0 for all omega, right? Or you add a phase shift in such a way that all frequencies or all omegas shifted equally in time. Right? You shift them all by the same amount so that the same square wave just gets shifted. I mean, all the frequencies are shifted so that you don't get a phase distortion, right? So in today's session we'll be discussing the first possibility, which is let us keep the phase shift to be 0. That is why the title of this topic is zero phase transfer function. The transfer function which does not change the phase of any component, which any frequency component, which means it does not change the phase of your signal. Okay, so zero phase transfer functions. So let us do some slight revision. We have a transfer function is h e to the power j omega, right? And if you pass a pure sinusoid or a pure frequency omega naught to this function, right? This is the pure frequency. So what you see here is h e to the power j omega naught gets multiplied. It's an eigen function of your transfer function, right? So basically this is the output, and this is consisting of two parts, the magnitude and the phase. So this is the gain, right? And this is the phase shift. Now for zero phase transfer functions, I want this phase shift to be 0 for all frequencies. So this means my h e to the power j omega should be purely real, but also it should not be negative, because if it is negative, then again the phase will be 180 degrees, right? So it should be real and non-negative. That is why h e to the power j omega should belong to R positive. Okay. So how do we design this? How do we design such a transfer function? So one possible solution is we want this kind of a transfer function which is zero phase. So this inverted cap represents zero phase transfer function, and it can be mod h1 whole square, where so whatever is h1 e to the power j omega, its mod square will always be purely real, right? And means it will be purely real and non-negative. So this is what is a possible solution. So basically what we do is we have an H, zero phase H, H inverted cap, which is H1Z times H1Z inverse. Here, H1Z should have real coefficients. Okay, I will derive this. How do we get this? So let us start from here. So you have H zero phase Z is equal to H Z times, I mean H1Z times H1 star of Z, right? This is the requirement. Now, I know if H1Z is, if it has all real coefficients, it's a rational form, let us say, it's a rational function. And if it has all the real coefficients, then what will happen? Just your e to the power j omega becomes e to the power minus j omega, and everything else is anyways real, so it doesn't matter. So this is equal to h1z. I should have written e to the power j omega. Let me do that. This will be equal to h1 e to the power j omega times h1 e to the power minus j omega, right? Because everything else is real. So therefore you get this. Start from here and you derive this. So this is one possible design. Now let us study some properties of this, that my zero phase transfer function can be written as product of h1z and h1z inverse. Okay, so let's first see graphically what happens. So my hz is basically equal to some h1z times h1z inverse, right? So let us say my h1z is some, just a single pole, 1 upon 1 minus, let's say z0 z inverse, right? This means this has got a pole at z0. Let us say here we have z0, right? This is my pole. Pole is represented with a cross. So this means my h1 or my h z zero phase z will become h1 1 upon 1 minus z0 z inverse times h1 of z inverse, which means if I replace this z with z inverse, which means my z inverse will become z 1 upon 1 minus z0 z inverse, right? So which means z, right? So what does this mean? This means this has got a pole at 1 upon z0, right? This term will become 0 at z equal to 1 upon z0. So this means I have got a pole at 1 upon z0. So what you find is that I get a mirror symmetry, which means if I have a pole at z0, I must have a pole at z0, 1 upon z0 as well, right? This is graphically the meaning. Now, let us consider a polynomial, which is basically if I say my h1z zero phase is some numerator, let me call it as some b1z upon b2z, then each of these b1 and b2 should also be should also have that property that they have pole which are mirror symmetric, and similarly the zeros which are mirror symmetric. So each of these polynomial has to be a symmetric polynomial. So what does that mean? It means now my bz will be of this form, that sum z to the power L plus z to the power minus L. So if this condition is satisfied, then I can assure that my BZ is symmetric, which means my B bar Z and B bar Z inverse, they should be same, right? So my B, I shouldn't call it bar, it's a B inverted cap Z is equal to B inverted cap Z inverse, right? Because you know this